Okay, today I'm going to show you guys how to use the ideal gas law to determine the molar mass of an unknown gas or its density. And you're going to have to bear with me for a second to allow me to substitute some things into this equation. Remember, this is PV equals nRT, pressure, volume, pressure times volume equals the number of moles of gas times the universal gas constant times temperature. And so what we can do is you have to remember, first of all, that if I said, okay, you have 24 grams of carbon, how many moles would that be? So we'll go back to our mole map. If you're going to go from grams to moles, you have to divide by the molar mass. So in order to do that, again, you would take our 24 grams of carbon, you're going to moles of carbon, over grams of carbon, 1 mole is 12 grams, so the answer there is 2 moles. But what this is telling us isn't, so what moles equals, it is the mass. So moles is equal to the mass of whatever it is you have divided by the molar mass. That's what gets us moles. Again, it was 24 divided by 12. So we can substitute this. We can substitute mass over molar mass in the equation for moles. And so that's going to allow us then, so that's what we've done here. So we've taken out N and we've substituted mass over molar mass. That's what capital MM is, molar mass. And then we can rearrange that equation. Again, we can move molar mass to the other side. If you are confused about how to do that, I'm just going to do this one time because it's something everyone needs to know how to do. I know I'm not your math teacher, and the way I'm saying this may not make a lot of sense to you, but this is the way I was taught 40 years ago. So we want to solve for molar mass in this. That's what we want to have the ability to do. So if you're going to move something to the other side, because we don't want to solve for 1 over molar mass, we want to move it to the other side, you have to multiply it by its reciprocal to move it. So you'd have to say molar mass over 1 here gets rid of there. Whatever you do on this side, you have to do on the other. And then also, we want to move pressure and volume to the other side so we can isolate molar mass. You would have to do the same thing over here. 1 over pressure and volume on this side to get rid of it, and then whatever you on one side you have to do on the other. So now that means our equation is molar mass is equal to the mass over pressure and volume. And again, you don't have to be able to do that. I'm just showing you why that equation is what it is. And so we can use this then to solve a problem where they're asking for the molar mass or the molecular mass of some gas. So we're going to use this for this equation here at the bottom. It says, what is the molecular mass of a gas of 20.6 grams? So its mass, again, is 20.6 grams in a 500 milliliter container at a pressure of 2,500 millimeters mercury and 350 Kelvin. So R, remember, is determined by the pressure units. And so pressure is in millimeters mercury. You can go back to the other page. R, when pressures in millimeters mercury, is 62.4. That's the universal gas constant. And temperature is already, temperature always has to be in Kelvin. It's already in Kelvin, so it's 350. Over pressure and volume, again, our pressure, 2,500 millimeters of mercury. And our volume in ideal gas law problems always has to be in either liters or decimeter cubed. They're the same thing. So 500 milliliters, you have to convert that to liters, and again, you can look it up. 1 liter is 1,000 milliliters, so 500 divided by 1,000, that is 0.5 liters. So don't forget, when you're doing ideal gas law problems, that volume always has to be in liters there. So we'll multiply across and divide with sig figs, our answer, and again, we're going to put a decimal there. We say we have 2 sig figs in our final answer, so 360. And that is grams per mole. That would be the molar mass. All right, moving on. You can also use the ideal gas law to solve for density, because here's the thing, when you're using this equation, density is mass over volume. And what we're going to do in this equation, notice we have mass over volume here. Get rid of them and substitute density in for that equation. And so we end up with density, or I'm sorry, we end up with molar mass now is density times universal gas constant times temperature over pressure. And so, but now, again, if we want to solve for density, we have to move density to the other side, and we'll manipulate this, or I'm sorry, we got to move everything else, your universal gas constant, temperature, and pressure to the other side of the equation. When we do that, that'll allow us to isolate density there, and so we end up with density equals molar mass times pressure over RT. You don't have to know how to do that. Again, I can show you by multiplying by the reciprocal how we can isolate density, but that's what's been done there to get that equation. So again, you always have these equations to refer to. Even if you moved up in the AP Chemistry and take an AP Chemistry test, you're going to have all these equations to do if you're taking the test or in that class. So anyway, so let me show you how to deal with solve for density from that equation there. And it says, what is the density of a sample of nitrogen gas that exerts pressure of 5.30 atmospheres, 3.5 liter container to 125 degrees Celsius. And the first thing we need there, and I've got to find my calculator, is the molar mass of nitrogen. I'm going to use the exact values from our star periodic table. So 14.007 times 2 is 28.014. So again, the molar mass of this gas is 28.014. The pressure is 5.3 atmospheres. We get that right there. Over the universal gas constant, and see our pressures in atmospheres. And when pressure is in atmospheres, again, R is 0.0821. Remember, the universal gas constant, it depends on what the pressure units are. And then that's times temperature, and temperature has to be in Kelvin. 125 plus 273 is 398 Kelvin. So you multiply across and divide, and you end up with 4.4 grams per liter. Anytime you get a gas density, the units would be grams per liter. All right, last thing there, last question for this stuff. You have two identical containers. One contains a mole of fluorine gas, the other contains a mole of oxygen gas. And you want to calculate, says which one would be more dense. I want to show you really don't have to do a problem for that, just it's common sense for this one. The equation for it, if we wanted to calculate density, is molar mass times pressure over RT. And it's saying that it says the containers have the same temperature and pressure. So all of these things are the same. All of those are the same. And so what you have to understand, then the larger the molar mass, the greater the molar mass, the greater the density. They are directly related to each other. So it should make sense. It should be common sense to you that the gas with the highest molar mass would have the greatest density. And F2 is a Brinkhoff element, weighs 38 grams per mole, and O2 is 32 grams per mole. So the correct answer there, the one that would be the most dense, would be fluorine, because it has a greater mass. All right, that's it for today. You got some go formative problems to work on. Good luck.